Hi Year 12, this is the first of 6 lessons for the topic of proof for Extension 2 Mathematics. In our first lesson, we're going to look at logic. Here's the lesson outline. We're going to look at language and notation of proof, logical connectives, negation, implication and equivalence, and then finally converse and contrapositive statements. Now, when we learnt about proof in Extension 1 Mathematics, we looked at what proof actually is. It is a correct argument which establishes the truth of a mathematical statement. It starts with an assumption or a conjecture. It has a sequence of correct mathematical steps with justification if needed, and it ends with a conclusion. So let's look at an example of a simple proof. Show that the sum of two odd numbers is an even number. We're going to start by defining two odd numbers. Now, the easiest way to define an odd number is either as 2m plus 1 or 2m minus 1. I need two odd numbers and they can't be related to one another, so I need different pronumerals. So I've got 2m plus 1 and 2n plus 1, and I need to also say that m and n are integers. Okay, we want the sum of those two numbers. So 2m plus 1 plus 2n plus 1, that's 2m plus 2n plus 2. And factorising our 2 out, we get an even number because m plus n plus 1 is an integer. And then just writing the conclusion, therefore the sum of two odd numbers is an even number. So let's move on. There is some new notation that we need to learn for proof. And the first part of it is these things called quantifiers, and there are two of them. The first one is for all. We can also say the words every or each or any, and we use this symbol upside down A. So this means for all. The other quantifier is there exists. We also say some or there is, and its symbol is a backwards E. So this is there exists, and this is for all. Remember that we have some specific sets of numbers. When we were doing complex numbers, you would have learnt that C is the set of complex numbers, R is the set of real numbers, Q is the set of rational numbers, Z is the set of integers, and N is the set of natural numbers. And here's an example of what we might write. N is an element of Z, and that means N is an integer. So let's have a look at how we might use those quantifiers and the sets. What does this say? For all N that are elements of the set of rational numbers, or for all rational numbers N is equal to P on Q, where P and Q are integers, and Q is unequal to 0. And that's actually the definition of a rational number, isn't it? How about this one? For all N that are positive integers, N is the sum of 4 square numbers. And this one? There exists an N that is a complex number such that, that's what that dot dot means, N squared is less than 0. That's true, isn't it? There is a complex number, I, such that when we square it, we get a number less than 0. Now, order is important with these quantifiers. So if the symbols for all and there exists appear in the same statement, then we need to be careful. Let's look at two examples where the order is switched around. Here's the first one. This says, for all n, there exists a k such that k is greater than n. Now that's a true statement. Can you tell why? For all n, whatever number you can think of, it doesn't even say what type of number, there exists another number, k, that is going to be greater than it. And that's true, isn't it? No matter what number we can think of, we can always think of a number bigger than it. What happens when we switch these around? There exists a k such that for all n, k is greater than n. And this one is not true. Think about why. There exists a k such that no matter what number we think of, k is always going to be greater than it. That's not true. Okay, so order is important. Okay, let's move on. A statement or proposition is a sentence that is true or false, but it's not both. And we say that it should have a well-defined truth value. It means it's either true or false, but it's not sometimes true, for example. I am a teacher. That is a true statement. Peas are legumes. Another true statement. The Eiffel Tower is in Germany. That's false, but it is still a statement or proposition. But this one, I like being a teacher. Okay, this one doesn't have a well-defined truth value because most of the time I like being a teacher, but sometimes I don't. Peas are delicious. This one is subjective. It depends on whose opinion it is. Now, statements that are true require a proof, and statements that are false require a counterexample. Now we use logical connectives to connect statements, and there are 3 of them. There's and, or, and not. A and B is true only when A is true and B is true. A or B is true when either A is true or B is true or both are true. And we sometimes call this an inclusive or because it includes both A and B being true. And the negation, not A is true when A is false. And this is what we write, this symbol here or this one here. Now an implication is a conditional statement and it combines 2 statements as an argument. It's also known as an if-then statement. If you've done any sort of computer programming, you'll be well aware of an if-then-else statement, which is very similar. But if not, it's fairly easy. This is what we write, A, and then an arrow like this, and then B. And this is what it means. A implies B, or if A is true, then B is true. Here's an example. If I eat my breakfast, then I won't feel hungry. Remember I said it's like an argument? This first part here is the premise or condition, and this last part here is the conclusion or the outcome. So which is the premise in the following? Because English can be a tricky language. Remember, we can switch things around, so you can't just memorize it as the first part of the sentence. Here's the first example. Whenever I exercise, I feel energized. So think about the thing that has to happen for the second thing to happen. So it's whenever I exercise, isn't it? That's the premise. For me to sing in the shower, I must be happy. So what has to happen? I must be happy. So there's an example of where it's going to be at the end of the sentence. I will use an umbrella if it is raining. What comes first? The rain. There's the premise. It is necessary that the diagonals bisect one another for the quadrilateral to be a rectangle. What has to happen? The diagonals must bisect one another. I think, therefore I am. Famous quote by Descartes. What has to happen first? I think. There's the premise. Now the converse statement is obtained by swapping the statements on either side of the implication statement. So if the statement is A implies B, the converse is just B implies A. Here's an example. Let's let A be the shape is a square and B is the shape has 4 sides. So the statement is if the shape is a square, then it has 4 sides. The converse statement is if the shape has 4 sides, then it is a square. So what do you notice there? The converse of a true statement is not always true. Did you notice that this one is not true all the time? If the shape has 4 sides, then it is a square. Not necessarily. It could be a trapezium or a rhombus or anything. Now, if a statement is true and its converse is also true, then this is called an equivalence. And we write a double-headed arrow to show that it goes both ways. We can say A implies B and B implies A. Or A if and only if B. There's the abbreviation of if and only if. Or A is necessary and sufficient. Necessary means vital. Sufficient means all that is required. So A is necessary and sufficient for B. Here's an example. It is a rhombus if and only if it is a plane shape with 4 equal sides. Here's an example. Are the following implications or equivalences? If 2x is equal to 6, then x is equal to 3. Now that's a true statement. To figure out whether that's an equivalence or not, we need to look at the converse statement. So let's turn it around. If x is equal to 3, then 2x is equal to 6. That is also true. So therefore, this first one is an equivalence. How about this one? It is a mammal if it feeds milk to its offspring. Now that's part of the definition of being a mammal, so that's a true statement. Let's look at the converse. If it feeds milk to its offspring, then it is a mammal. Now that's actually not true because there are some non-mammal animals like spiders that do secrete milk for their offspring. So this one is an implication, not an equivalence. And finally, if I can see the Eiffel Tower, then I am in Paris. That's a true statement. Let's turn it around. If I am in Paris, then I can see the Eiffel Tower. Now that one's not necessarily true because we might not physically be near the Eiffel Tower. So that last one there is also an implication, not an equivalence. Now be careful of using the equal sign instead of the equivalent sign. We use the equal sign to write the two expressions are equal to one another like in an equation. But this one here, we use to write that two statements are equivalent. So here's an example where I'm using an equal sign and an equivalent sign. C squared is equal to A squared plus B squared if and only if the triangle is right angled. Before we move on to contrapositive statements, we're just going to briefly look at negation. The easiest and best way to form a negation is just to use the word not in the statement, but it's important where you put it. Let's write the negation of this statement. Susan is a swimmer. The negation is simply Susan is not a swimmer. But this one, x is greater than 3. X is not greater than 3. Or we could turn it around and write x is less than or equal to 3. And finally, Jim knows everything. What do you think the negation is here? Do you think it's Jim knows nothing? It's not actually. It's Jim doesn't know everything. So the contrapositive statement is obtained by swapping the statements on either side of the implication symbol, just like we do for the converse, but then we also negate them. So we've got one extra step. So if the statement's A implies B, the contrapositive statement is not B implies not A. So here's an example. If it is my birthday, then I will open some presents. The contrapositive statement is going to be, if I'm not opening some presents, then it is not my birthday. Now what do you notice about that? If this first statement is true, if it's my birthday, I'll open some presents, the contrapositive statement is also true. If I'm not opening presents, it's not my birthday. And that's different to the converse statement. Converse statement, remember, sometimes it's true, sometimes it's not. In this case, if I'm opening some presents, then it is my birthday. What do you think about that? That's not always true, is it? It could be Christmas. So in this case, the converse is not true all the time, but the contrapositive is. Which brings us to an important point. The contrapositive statement is logically equivalent to the statement itself. And all that means is, if the statement is true, then the contrapositive statement is true. We just saw that. If the statement is false, the contrapositive statement is false. Let's have a look at an example of a false statement. A number is even if it is not divisible by 2. That's false, isn't it? Let's form the contrapositive statement. We are going to negate this. We're going to be a double negative, not divisible, which means is divisible, and not even. So our contrapositive statement is, if a number is divisible by 2, then it is not even. And again, that is a false statement. Here's a past exam question. The sign shown appears on the rear of large vehicles. If you can't see my mirrors, I can't see you. You might have seen that on trucks in Australia. Which of the following statements is logically equivalent to the statement on the sign? Logically equivalent means contrapositive. So we just need to switch these two around and negate them. So we're going to take the I can't see you and put it first and negate it. And then if you can't see my mirrors, we're putting that second and we're going to negate it. Now, the negation of I can't see you is I can see you. And the negation of you can't see my mirrors is you can see my mirrors. So the contrapositive statement is if I can see you, then you can see my mirrors, which is B. Now there are some tricky rules with negation. The first one is the negation of an and or statement. And the negation of A and B is not A or not B. So and becomes or. Here's an example. Suppose we've got x is greater than or equal to 9 and x is less than 11. So let's just draw that quickly. So we've got greater than or equal to 9 and less than 11. So it's pointing in. this way. The opposite, or the negation of that, must be what? Pointing out. Can you see how it's becoming an or statement? So the opposite is going to be x is less than 9 or x is greater than or equal to 11. And the negation of A or B is not A and not B, so or becomes and. Here's the statement. A is a cat or B is a dog. The negation of that is A is not a cat and B is not a dog. The negation of a for all statement is a there exists statement. This says for all n that are real numbers, n squared is greater than or equal to 0. The negation of that is there exists a real number n such that n squared is less than 0. So for all becomes there exists, and I've negated the second part. About this, all cats are friendly. The negation is not all cats are friendly, or there exists at least one cat that is unfriendly. The negation of a there exists statement is a for all statement. This says there exists an integer n such that 3n is equal to 6. The negation of that is there doesn't exist an n such that 3n is equal to 6, but we probably should write for all n that are integers, 3n is not equal to 6. And finally, some maps are accurate. The negation of that is, you can see how this is a there exists type statement. So the negation is there are no maps that are accurate, or all maps are inaccurate. And finally, the negation of implications. The negation of if A then B becomes if A then not B. Write the negation of if x is irrational then x squared is rational. We leave the first part, the premise, alone. We negate the conclusion. If x is irrational, then x squared is not rational or irrational. Now you need to be careful when you get worded statements, particularly if they've got for all or there exist type statements in them. Whenever I eat my breakfast, I always feel energetic. So this is a for all type statement. So the negation in this case is not going to be when I eat my breakfast, I don't feel energetic. I need a there exists type statement here. And one of the best ways to do it is to put it into the past tense. There was a time when I ate my breakfast and I didn't feel energetic. Here's a past exam question. Consider the statement, if n is even, then if n is a multiple of 3, then n is a multiple of 6. Which of the following is the negation of the statement? Now this one's a bit confusing because it looks like it's got 3 parts. If n is even, then if n is a multiple of 3, then n is a multiple of 6. But actually this part here is the premise. Okay, it's basically saying if n is even and if n is a multiple of 3, then n is a multiple of 6. So here's our premise. We'll call it P, and here's our conclusion. We'll call this one Q. So to get the negation, we want to leave the premise alone and we want to negate the conclusion. All right, let's have a look at these answers. If n is odd, okay, that's negated the premise, so that one's out. If n is even, yep, n is a multiple of 3, yes, but not a multiple of 6. Actually, it's B, isn't it? Let's just have a look at C and D and see what's wrong with them. N is even, yes. N is not a multiple of 3, no. And then finally D, n is odd, so that one's out. So our answer is B. Okay, let's see if we can tie this all together. For the statement below, write the converse, contrapositive, and negation. If the animal is an elephant, it washes itself with its trunk. The converse is easy. We switch the two statements around. If the animal washes itself with its trunk, then it is an elephant. Contrapositive, switch them around, negate both of them. If the animal does not wash itself with its trunk, it is not an elephant. And then finally, the negation, we leave the first part alone and we want a there exists statement to the end of it. So there is an elephant that does not wash itself with its trunk, or there exists an elephant. Okay, a bit of fun to finish off. Charles Dodgson, better known as Lewis Carroll, who wrote Alice in Wonderland, was actually a mathematician, and he wrote a book about mathematical logic, and it was called The Game of Logic. And here's one of his classics. Babies are illogical. Nobody is despised who can manage a crocodile. Illogical persons are despised. What's the conclusion? Have a think about it. I'll tell you in the next lesson, which is on direct proof.